a new chapter, chapter 16, which is on vector calculus. So section 16.1, vector fields. So a lot of this first section will just be terminology. So if F goes from R2 to R, then this is called a scalar field. And so I can think of it at every point. Let's say you have some laminar plate, and I want to figure out the temperature at every point in the plane. Well, that's a scalar field. So for every point in the plane, there's a particular temperature. F going from R2 to R2 is called a vector field. So at every point in the plane, if I have some vector associated with it, then I called it a vector field. Such as, suppose you have a magnet. Again, let's say you have a magnet underneath some aluminum sheet or some sheet. And let's say that you put some iron filings down on the sheet. If you put a magnet underneath it, what you'll notice is that they all orient in a certain fashion, and they each have this sort of, so there's some vector that's associated with every point in the plane. From R3 to R3, well, that's a vector field on R3. So in general, if I have a function f going from R2 to R, then if I look at the gradient of f will then be a, okay, good, will then be this sort of vector that is associated with every point in the plane. And so we'll call this, we will associate with this a gradient vector field. So this is a vector field, and we'll call it, so associated with this gradient will be a vector field, and we'll call that a gradient vector field. A vector field is called conservative if there exists some function f called the potential function of capital F, let's say, such that f is equal to the gradient of little f, or negative the gradient, depending on the negative in front of it, in front of the potential function, in front of the gradient. F, but in mathematics, we don't have a negative sign. F going from Rn to R is called a scalar field on Rn. And so at each point in space, you have some single scalar quantity. So let's say temperature. So if you're in some dimensional, n-dimensional space, then let's say that at each point in that space, you have some sort of quantity temperature that you're measuring. And that is just, and if you notice, temperature is just a number, it's a scalar. And so if I go from Rn to R, we call that a scalar field. If we go from Rn to Rn, we call it a vector field on Rn. Let me discuss differential forms, which will help us to notationally to look at vector in a fashion where all of these formulas that I'll be giving you all turn out to be the same thing when looked at in a certain fashion, and they all fall out from rather simple. And so this construction, given algebra, which give us some sort of algebra, exterior algebra, unify the concepts that we're going to be discussing. Okay, so differential form. F of x1, x2, x3, all to xn is called a zero form on Rn. So f is just a function. So a function, a zero form on Rn, any zero form is just a function. Usually, we want these to have nice properties, so we'll usually assume that they have continuous partial derivatives up to whatever order we wish to. So basically, usually arbitrarily large continuous partial derivatives. So we don't have all those problems that we had in previous chapters dealing with existence and continuity and all that when we didn't have assuming continuous partial derivatives. Usually, in differential forms, rather than having subscripts, usually we have for the x's. For these, we write them as superscripts. So this is the same as x1, y1, x of 1, x of 1, x of 2, x of 3. It just happens to be that I'm writing them with superscripts. So the function f of x is a zero form on R. So a zero form on R is just some sort of function. The sum of f sub I of x of 1 through x of n dxi for I going from 1 to n is called a one form on Rn. So an example of a one form on R2 is f xy dx plus gxy dy. So that is a one form on R2. Let me give you an example, a specific example of a one form on R3. P, for some reason, usually we use, especially in R3 for one forms, P, Q, and R for the names of our functions, but that's just what we call our functions. So P, x, y, z, dx plus Q, x, y, z, dy plus R, x, y, z, dz. This is a one form on R3. So any one form on R3 will look something of this type. The sum over ij, fij, x1 through xn, dxi, wedge, dxj is called a two form on Rn. I'll be telling you what wedges are in a second, but the sum over I, f sub I, x1 through xn, dxi is form on Rn, where I is a subset, I sub 1, I2, dot, 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 IP of 1, 2, dot, 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 n, and dxi is just dx I1, wedge dx I2, wedge dx I3, dot, 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 wedge dx IP. If omega is, and usually many a times, we will denote these K forms or P forms with a Greek letter. If omega is a P form, then we say that omega has degree P. So now the important properties. Let alpha, beta, gamma be differential forms, not necessarily all of the same degree, but they're not non-zero degree. So be a zero form. Then alpha plus beta wedge gamma is alpha wedge gamma plus beta wedge gamma. And so this distributes. And so again, the wedge product distributes. It acts like a product. So a wedge product distributes over addition. Alpha wedge beta plus gamma is alpha wedge beta plus alpha wedge gamma. The wedge product is associative. Alpha wedge beta wedge gamma is the same as alpha wedge beta wedge gamma. And so usually we do not put parentheses around these because they're associative. So since they're associative, we don't need any sort of parentheses. If C here, again, is a constant, it's a scalar, it's a zero form, then I can just take it out of the wedge product. So if I have alpha wedge beta, that's the same as, well, I can bring it over here, alpha wedge C beta, and it's equal to, well, I can bring it out in front of the wedge product, C alpha wedge beta. So if you have any constant in any, zero form, you can just bring it out in front of the in front of this wedge product. So basically this says that dealing with wedge products, you do what you normally think you should do with a product. And so it acts like a product. So just think, well, the wedge product acts like a product. So these properties, very important, are very understandable. Next, that alpha be a K form and beta be an L form. Then alpha wedge beta is -1 to the power KL times beta wedge alpha. So this says that this product is not commutative. So everything works, but be careful with changing the of the with the wedge product. So you have to multiply by this by -1 to the product of the degrees of these differential forms. Now, in particular, if I have one forms, well, 1 times 1 is just 1, so -1 to 1 is a negative. Therefore, if I have, let's say, the one form dx wedge dy, that's just equal to negative dy wedge dx. And so that means that if I change the order of these D's, then all of a sudden, well, if I just permute two of them, then the sign changes. Okay. This implies that, well, if you had an x here, you'd have dx wedge dx is minus dx wedge dx. And so if you added the dx to both sides, you'd have 2 dx wedge dx is 0, divide by 2, so dx wedge dx is 0. And so you can do that same sort of permuting. You may have some signs, but you can always keep permuting so that if you happen to have in a list of D's, 2 D's that are the same, like 2 DX's or something, then the product, then that differential form is going to be 0. So if I equaling I sub 1, I sub 2, dot, 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 I sub p, is a list of indices where some index gets repeated. So, maybe one of these are the same. Then dxi is just 0. So if you have a whole bunch of d's and one of them is the same, well, you can just get rid of that. You can just disregard that term. So that will simplify our algebra. So basically do algebra the same way you've always done your algebra. Be careful, however, with the order of things involved with wedge products. If you have any repeats, those you just eliminate, and magically all of this chapter just becomes part of that little algebra. So the wedge product. So let me give you a little bit more about the wedge product. If alpha is equal to the sum over I, alpha sub I, x dx superscript I is a K form, and beta equaling the sum over j, beta sub j at x dx with the index j is an L form. Then define the k, this is a K form, plus L, this is L form. So you just add up the 2 degrees and you get a K plus L form. We'll define the wedge of these two differential forms as alpha wedge beta is the sum over I and j, alpha sub I times beta sub j times dxi wedge dxj. In particular, let's look at it, the wedge product, not even for differential forms. Let's look at it for any sort of vector. So if I had a vector in Rn, then we can define the wedge product of these two vectors as follows. It's just 1/2 the transpose of U times V minus V transpose times U. So this exterior, well, the exterior product. So it's the difference of these two exterior products. If we remember back, like the first week class, we looked at the inner product, and associated with that, there was a outer product. So this is the involving the outer product. So I can define this as, so the wedge squared R sub Rn is just the set of skew symmetric n by n matrices with real coefficients. So we have that the transpose of A is equal to negative A. I can define for any vector space V, this is equaling the sum over I, U sub I wedge V sub I, where UI and VI are in the vector space V. I can do this for 3. It's just the sum over I of UI wedge VI wedge, say WI, where UI, VI, and WI are in this vector space V. The exterior derivative. The exterior derivative is defined as follows. If alpha is equal to the sum over I, alpha I, dxi, is some k form, then I'll define the exterior derivative as, so it'll be a k plus 1 form, as d alpha is equal to the sum over I and j. Notice that j here is just a single index, not a multi, and I here is your multi-index. Partial alpha sub I at x with respect to x of j times the wedge product dxj wedge dxi. Let me give you some properties. So what I will say is, even though I haven't given you, I've only given you barely any definitions, because the definitions are particularly horrible. And so I won't really give you all the definitions. But the important things are not the definitions, but the properties. And once you, and the properties are easy. And once you know the properties, you can then, from there, because it's a nice, easy formulas. Okay, so property of exterior derivative. If alpha is a K form and beta is an L form, then the exterior derivative of alpha wedge beta is, well, just use Leibniz rule. So this is a Leibniz property, Leibniz rule. It is just the exterior derivative of wedge beta plus negative 1 to the k alpha wedge the exterior derivative of beta. Next, the exterior derivative of the exterior derivative of alpha is just 0. So note that we usually denote this fact as follows. So this is usually written as d squared equals 0. So a lot of times I might write that, or you'll see that written. So let's look at some examples. Exterior derivative is, well, df. So let f be a 0 form on R1. And so let's look at df. So if f is a 0 form, then the exterior derivative of this 0 form on R1 is just, well, the regular derivative of f at x times dx. And so you'll see that this looks very familiar. So this looks like something we've seen before. dy equals y prime dx. So this is something we've seen before. It's the differential. So it's the differential that we've we're familiar with from Calculus 1. Let F, and what you'll notice is that a lot of these formulas that we'll be getting are going to be very similar to things that we've seen before or that we will be seeing in the near future. Let F be a zero form on R2. Then dF is equal to the partial of F with respect to x dx plus the partial of F with respect to y dy, the total differential. Let F be a zero form on R3. Then the exterior derivative of this zero form on R3 is just the partial of F with respect to x dx plus the partial of F with respect to y dy plus the partial of F with respect to z dz. Again, this is just the total derivative. Note that dx is just equal to, well, the partial of x with respect to x, 1 times dx. So the exterior derivative of x is just dx. And so, therefore, this notation is what you would think it should be. Okay, let's do some examples on page 1113. In problems 21 through 24, find the gradient vector field of F. So problem 24, F of x, y, z is equal to x squared y e to the y z over z. So let's determine the gradient. So the gradient here is equal to, well, let's take the partial with respect to x. The partial of x squared is 2x times the constant y e to the y over z. Let's take the partial with respect to y. So I'm going to have to use the product rule. So the derivative of the first, the derivative of the constant x squared times y is x squared times the second, e to the y over z, plus the first, x squared y, the constant, the first, x squared y, times the second, the derivative of the second, the derivative of e to any exponent is e, and so e to the y over z times the derivative of the exponent. Well, the derivative of y divided by the constant z is just the dividing by the constant z. Next, let's take the partial with respect to z. And so it's the derivative is just the constant x squared y times the derivative of e to the exponent times the derivative of the exponent. Well, the derivative of the constant y is just y, so this becomes y squared, times the derivative of x of z to the minus 1 is just a minus z to the minus 2. And that is your answer. And so I get that the vector field, well, therefore the gradient vector field is just the following mapping. You just take, well, x, y, z, and you map it to, actually, let's make it easier. Yes, I can cancel, 2xy, x squared plus, actually, I can probably factor out x squared here, x squared 1 plus y over z, and a negative x squared y squared over z squared e to the y over z. And let me check the question. How did you get the derivative with respect to z? Oh, okay. So derivative with respect to z, remember that x squared y is a constant, and this is just y z to the negative 1. So to take the derivative, let's actually, let me get that. Let's get some extra room here. So let's say that I want to take the derivative of this with respect to z. Well, this is a constant, so I don't do anything with this guy. Now, the derivative of e to any exponent is e to that exponent times the derivative of the exponent. Well, y is a constant, and the derivative of z to the negative 1 is a negative z to the negative 2. And now I just multiply the x squared y times my y, so that it becomes y squared. I brought the negative outside, and instead of writing z to the negative 2, I wrote it as dividing by z squared times e to the whatever. And so that was your derivative. Okay? So that's how I took the derivative. Any other questions about that? Okay, good. Okay, so now let's do the next example. Okay, 1 second. Okay, so simplify the wedge product of the following one forms on R2. So I have this one form, wedge this one form. So let's multiply this out. So by the properties, well, again, the wedge product just acts like a regular product. And so by the distributive property, we can just write this as 3 dx wedge e to the x dx plus 3 dx wedge 2 dy plus dy wedge ex dx plus dy wedge 2 dy. So let's simplify this. Well, again, I can take out all constants, all zero forms outside of wedges. So let's take all the zero forms outside my wedges. So 3 e to the x dx wedge dx plus, again, bring out the zero form. So 3 times 2 is 6 dx wedge dy plus bring out the e to the x dy wedge dx plus 2 y wedge dy. Okay, let me add another. Okay, come on. There, thank you. Come on. Let me add another page. Okay, so, oops. Wouldn't you know it? Okay, so let's add another page here. So, first off, note that if I have dx wedge dx, that's 0. So this guy here goes to 0. And this guy here goes to 0 also, a dy wedge dy. So anything that's repeated, I know that that's going to be 0. Okay, so this is equal to 6 dx wedge dx, dy, sorry, plus e to the x dy wedge dx. Okay, so now, if you look at these look the same. I just have a differing order. So let me interchange the order here. Somehow, let's try to interchange the order. And when I do that, I'm going to change the sign. So this will be a minus ex dx dy, wedge dy. And so my final answer is 6 minus e to the x dx wedge dy. Okay. And so I have just used the algebra. And you notice the algebra is basically the same algebra we have with just dealing with, regular multiplication. But be careful about the order when you are doing the wedge product. And so when you have the wedge product of any of these differentials, these d's, then you have to be sure that use the fact that this is skew symmetric. Okay. Next. Oh, notice that when working on Rn, there are exactly in CK linearly independent d sub i's, di's of degree k. And so we will usually use a standard ordering for I. And so notice that rather than leaving it in this form, x wedge dy and a dy wedge dx, I changed it so that my final answer at the end had the ordering x before y. So there's usually some sort of ordering that we are comfortable with. And, well, there could be an orientation that we wish to preserve. Okay. Note the differential forms of degree greater than n are equal to 0. And so if I have a differential form on R2, I won't be really, a 3 form on R2 is going to be 0. So we usually look at things that are less than that. Otherwise, they're going to be trivial. Okay, so let's do another example. Compute the exterior derivative of the following one form. So I want to get a two form. And so, well, my answer will be a two form. And so omega, well, the differential here. So let's find the exterior derivative. So the exterior derivative is just, well, the partial, I don't know. Yeah, maybe I'll write this way. It's just the partial, the sum. Well, let me just do for this one. So it'll be the partial of this component with respect to x of dx wedge dx plus the partial of this first component with respect to y, dy wedge dx plus the partial of this next component with respect to x dx wedge dy plus a partial of this last component with respect to y of dy wedge dx. Dy, sorry about that. Dy wedge dy. So that's just using the definition of the exterior derivative. So this is equal to, so d omega is equal to, so let's take the partial of this first respect to x. So that'll give me a y dx wedge dx take the partial of this guy with respect to y. So that'll give me an x dy wedge dx. So this says that I took the partial with respect to x. This says that I took the partial with respect to y. So I took the partial of this guy with respect to y. Let's take the partial of this with respect to x. So I have to multiply by dx wedge dy plus the partial of this with respect to y. That's like I give you a whole lot. 0 dy wedge dy. So let's go back up here for 1 second and explain. So now that I haven't finished this one yet, but see this notation. So now notice that I'm taking the partial with respect to each of those components of my differential form with respect to each of those. Oh, I should have called this x sub j as a superscript j because I'm using superscripts. So I took the partial with respect to each of the variables. And when I did that, I multiply by d of that variable, wedge everything else. So wedge all that other stuff of all those other d's of x's. Okay. So let's finish this off. Now here it is. So first off, dx wedge dx, that's 0. So this guy is 0. This guy obviously is 0. Well, doesn't matter. I already have a 0 there, but so this guy is 0. So I get this is equal to So the exterior derivative, a w, is equal to x raised hand. Okay, well, let's just see. How do you know what form to use? Oh, you mean if I'm in the example, it said that I was taking the exterior derivative of this. How do I know, like the one form? Yeah. So it was given. It was given in the example. Now, in the next section, we're going to be integrating one forms, and those are going to be called line integrals. Okay, so we'll be integrating those. Okay, so that's 0. Okay, so this is dy wedge dx plus ex dx wedge dy. And so the exterior derivative of the one form omega is equal to, well, I have an ex dx wedge dy. And let's change the order here. So this will become a minus x dx wedge dy. And again, I usually write x before y. And that is your answer. Okay, so that finishes off section 16.1. We'll be doing a whole bunch more with differential forms in the next few sections, where I first do it sort of reformulate it. That's strange.